Assalamualaikum and hi. Today we'll be talking about thermodynamics application, a comparison between nanotechnology and Hvac system, presented by Group 3. This is our team member, which consists of 4 people.
Alright, so I'm Kelvin, now going to start with the problem statement. In this topic, we have 3 problem statements. So first of all is the thermal management. Okay, the first point is about the zeroth law of thermodynamics. So the zeroth law of thermodynamics states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. This law established the concept of temperature and formed the basic for defining temperature scale. Yeah. So for the nanotechnology, okay, in the nanotechnology, where precise control over temperature is crucial, the zeroth law ensures uniformity and consistency in thermal equilibrium. For instance, when designing nanomaterials for electronic devices, ensuring that different components are at the same temperature is essential for reliable performance. By applying the zeroth law, engineers can ensure that nanoscale systems operate under well-defined thermal conditions, which allow the predictable behavior and efficient energy management. Okay, so apart from nanotechnology, we have HVAC system. Okay, in HVAC system, the zeroth law is foundation for establishing the concept of thermal equilibrium within a building or a space. This law ensures that different zones within a building reach a consistent temperature, providing thermal comfort for occupant. Okay, and then this design enable for the control system maintain in a uniform temperature throughout the space to prevent from hot or cold spots. Okay, by applying this zeroth law in HVAC system, engineer can design system that efficiently distribute heat or cold air to achieve desired comfort level when minimizing energy consumption. Okay, so now I'm gonna to going on for the second problem statement, which is the energy conservation principle. Yeah, so first we go into the definition for the first law of thermodynamics. So the first law of thermodynamics states that energy cannot be created or destroyed, okay, but energy only can transform from one form to another form. So this will apply in the nanotechnology and HVAC system. For the nanotechnology, the first law of thermodynamics governs the transformation of energy at nanoscale. For example, in nanomaterials-based energy storage devices or nanoscale electronic component, energy conservation process such as charging, discharging, and electrical energy conversion, okay, must comply with the first law. So with the first law of thermodynamics, and then the engineer can use this law to optimize the efficiency of energy conversion processes and minimize energy loss to the surrounding and provide a good performance for the nanotechnology devices. So apart from that, we have HVAC system, which also apply for the first law of thermodynamics too. So in HVAC system, the first law of thermodynamics governs the transfer and transformation of energy involved in heating, ventilation, and air conditioning process. For instance, during the refrigeration cycle, energy is transferred from the indoor environment to outdoor environment, which is in cooling mode, or vice versa in the heating mode. This first law of thermodynamics ensures that the total energy inputs to the system equal to the total output, okay, accounting for changes in internal energy and the work done by or on the system. Okay, apart from that, the first law of thermodynamics in this HVAC system also guides the design and optimization of HVAC system for energy efficiency. Throughout this process, engineers can analyze the energy balance within the HVAC system to identify opportunity for improving efficiency, such as reducing the heat loss and minimizing energy consumption of compressor and the fans by optimizing the utilization of renewable energy sources. So the third problem statement is the heat transfer performance. It is related to the second law of thermodynamics. The second law of thermodynamics states that it introduced the concept of entropy, which essentially quantifies the degree of disorder and randomness in a system. For the nanotechnology, the second law of thermodynamics serves as a guiding principle for understanding and minimizing entropy generation. Throughout this law, engineers and researchers in nanotechnology strive to minimize this entropy generating process to maintain the desired functionality and stability of nanomaterial and devices. For example, in the design of nanoscale electronic devices, to minimizing entropy generation is essential for reducing noise and improving signal-to-noise ratio. Then we will go into the HVAC system. In HVAC system, the second law of thermodynamics is particularly relevant to the efficiency of heat transfer process. According to this law, heat will flow naturally from region of higher temperature to a region of lower temperature, and the efficiency of this heat transfer process is governed by the temperature difference between the two regions. Within the law, The HVAC system engineers can aim to minimize entropy generation by optimizing heat transfer process, like insulating ducts and pipes, and selecting efficient heat exchange material. Moreover, the second law of thermodynamics also motivates the development and adoption of energy-efficient HVAC system technology such as heat pumps and thermal energy storage system to utilize temperature difference to perform useful work by minimizing entropy generation. Next, the objective of this topic is to assess the energy efficiency, which is to compare the energy efficiency of HVAC system with and without nanotechnology enhancement. Second is to evaluate heat transfer enhancement, like to conduct experiment or stimulation to compare the heat transfer rate using traditional fluids and nanofluid in the heat exchanger. The third one is to investigate the material properties, like to study the mechanical properties, thermal stability and corrosion resistance of nanomaterial for thermodynamic application, and to compare the durability and longevity of HVAC system, HVAC component with the traditional materials. Next is the hypothesis. So we have two hypotheses. The first one is, as compared to the standard HVAC system, the energy efficiency of HVAC system can be significantly increased by utilizing nanotechnology. Second hypothesis that addition of nanofluids in heat exchangers can increase heat transfer rates and improve overall system performance in thermodynamics applications.
Assalamualaikum and hi, my name is SAIFUL bin SAILAJA, and today I will be talking about findings regarding thermodynamics application in HVAC system. First things first, what is HVAC? Well, it is a heating, ventilation and air conditioning system which is used to control the temperature inside of a closed space. This can be done due to the thermodynamic effect that this system utilizes, such as the heat transfer, although there are some methods implemented into this system to fully utilize its potential. But before we dive further into the findings, I would like to share regarding the HVAC system advantages and limitation, with advantage being energy efficiency. By using thermal insulator and heat recovery ventilation, it can significantly reduce the energy usage of the system by being efficient in thermal management. For its limitation, HFC is a common gas used in the system due to its properties and safety profile, but it is bad for the environment and will have an environmental impact such as ozone depletion. This means that it is happening because of the HFC gases that is being released into the atmosphere. The other is the maintenance cost of HVAC system, as it is made of many components that require special skills and knowledge to operate, resulting in the need of specialists to properly maintain it. The first part of the finding that I will be talking is the thermal management, which is important to ensure the system operates efficiently by preserving the heat inside of the space from going outside. This is important to lower the cost of operating the system. By minimizing the heat loss to the surrounding, the cost will be lower, and this can be achieved by implementing thermal insulator to the space as it reduces the effect of Zeroff law of thermodynamics between the space and its surrounding. Next is the heat recovery ventilator, also known as HRV, which uses heat exchanger to exchange the heat of the incoming air with the outgoing air to minimize the energy need to cool the incoming air by utilizing the second law of thermodynamics. Lastly is the material heat conductivity, which shows the ability of a material to conduct heat. HVAC uses material with high conductivity, such as aluminium, as it helps in efficiently transfer the heat, especially at the heat exchanger or evaporator coil, where the heat will either cool or heat up the air. Lastly is the energy efficiency of the HVAC system. This can be achieved by using high efficiency equipment such as variable speed motor, which is able to change its speed based on the desired temperature of the space, providing a precise control resulting in a lower energy consumption of the system. Second is by using equipment with excellent SAER and AFUE ratings. The seasonal energy efficiency ratio (SAER) and annual fuel utilization efficiency (AFUE) ratings of an equipment is very important to consider in a HVAC system, as it shows the energy performance of the equipment. That's all from me. Thank you.
Okay, for the next second point in the findings about nanotechnology. So nanotechnology operates on the principle of manipulating matter at the nanoscale, typically between 1 to 100 nanometers, when unique physical, chemical and biological properties emerge. By controlling the structure of material at the atomic or molecular level, nanotechnology enables the creation of novel materials that devices with enhanced performance, such as increased strength, lighter weight, improved conductivity and greater reactivity, which are attainable to bulk materials. This precise control allows for groundbreaking advancement across various fields, including medicine, electronics, energy and environmental science. The addition of nanofluids in heat exchanger is a significant advancement thermodynamic application. offering substantial improvement in heat transfer rate and overall system performance. Nanofluids are suspension of nanoparticles such as metals, oxides, carbides, or carbon nanotubes. In conventional heat transfer fluids like water, ethylene glycol, or oil, these nanoparticles have much higher thermal conductivity compared to base fluid, facilitating more efficient heat transfer from the hot surface to the fluid and enhancing the overall heat transfer coefficient. The presence of nanoparticle increase the thermal boundary layerness, improving the convective heat transfer coefficient and leading to better heat transfer performance in both laminar and turbulent flow regimes. The Brownian motion of nanoparticles within the fluid help to disrupt the thermal boundary layers, further improving the heat transfer rates. The nanofluids can exhibit higher specific heat capacity compared to the base fluid and allow tunneling. It is allowing them to store and transfer more thermal energy per unit mass. This is particularly beneficial in applications that requiring significant energy storage and transfer. So the nanoparticle can modify the surface of properties of heat and quantum dots. There are semiconductor particles that exploit quantum tunneling for application in performance and quantum computing and advanced display. So next, some nanofluids possess anti-corrosive properties that which is protect the basic units of quantum and extend their operational life. Quantum tunneling and conducting qubits rely on the tunneling development of stabilizing tunneling field agents that prevent the aggregation and sedimentation of nanoparticles. Tunneling field effect long leverage quantum tunneling to reduce power consumption in electronic devices. So it's offering a path towards more energy efficient and durable. And the fourth one is about advanced materials. Innovation in materials such as carbon nanotubes and graphene have led to the development of resistors with improved performance characteristics such as lower noise and higher stability, energy savings, and reduced operational costs. By improving heat transfer rates, nanofluid contributes to the overall efficiency of thermal system, leading to better performance in heating, cooling, and power generation applications. Nanofluids are versatile and can be used in various types of heat exchanger, including shell and tube, plate, and fin tube exchanger. They are applicable in various industries such as Hvac, automotive, aerospace, and electronics. Novel materials like graphene and topology. The nanofluids can exhibit higher specific heat capacity compared to the base fluid. It is allowing them to store and transfer more thermal energy per unit mass. This is particularly beneficial in applications that requiring significant energy storage and transfer. The nanoparticle can modify the surface of properties of heat is not only a exchanger materials using polyanalytical perspective, but also driver of innovation across multiple technological domains. So some nanofluids possess anti-corrosive properties that which is protect the heat exchange surface and extend the operational life. So in advance,
Assalamualaikum and good day. My name is Dayana Nhatasya and I'll be explaining about the implication. The implication will have two parts, that is, the potential benefits and the challenges and consideration. There will be 5 potential benefits for nanotechnologies. The first one is developing nanomaterials with specific properties, that is understanding the relationship between structures and properties. For example, understanding the thermodynamics of self-assembly allows researchers to design nanostructures with certain shapes and sizes for application in medicine delivery, solar cells, and electronics. The second one is controlling chemicals reaction at the nanoscale, that is optimizing reaction rates and efficiency. Understanding reaction thermodynamics, for example, aids in the synthesis of nanoparticles of precise sizes, morphologies, which is critical for catalysis and sensor development. The third one is enabling bottom-up manufacturing, that is self-assembly and directed assembly. This bottom-up technique enables the development of complex nanodevices with precise control over their properties, possible changing industries such as electronics and medicine. The fourth one is understanding stability and performance of nanomaterials, that is predicting long-term behavior. This information is critical for applications such as nanomedicines, where stability is required for the safe and effective delivery of medications throughout the body. And the last one is developing nanoscale energy conversion technologies, that is harnessing thermal and solar energy. Particles with precise optical properties can be engineered to absorb sunlight and convert it into electricity more efficiently, helping to create a more sustainable future. Meanwhile, for the HVAC system, it has 4 potential benefits. That is, the first one is the improved heat transmission. That is, decreased energy consumption. Due to the increased heat transfer efficiency, less energy is required to reach the specified temperature. This results in less of an impact on the environment and less building operation costs. And then, enhanced system performance. Quicker heat exchange can result in more temperature control in buildings and faster reaction times, which can make the occupants more comfortable. The second one is cutting-edge thermal control. That is, diminish system dimension. It may be possible to make heat exchangers and other components lighter and small with enhanced heat transmission capabilities. As a result, HVAC systems can now be smaller and simpler to install in building. And then greater applicability. Nanofluids may be able to facilitate effective heat transmission in systems that are now constrained by weight or size, including building ventilation systems or portable air conditioners. The third one is innovative heating and cooling systems, that is light-based thermal control. First of all, the solar heating. By absorbing particular solar wavelength, nanoparticle may be able to heat buildings specifically, lessening the need for conventional heating systems. And the second one is the solid-state cooling. Infrared emitting nanomaterials may be utilized for solid-state cooling, which could provide a more energy-efficient option than conventional vapor compressed cycles. And the last one, it improves sustainability. It reduces reliance on traditional refrigerants. That is, as we know, current refrigerants used in HVAC systems can have negative environmental impacts. Nanotechnology may lead to the development of more environmentally friendly refrigerants with lower global warming potential, GWP. This could significantly reduce the environmental footprints of HVAC system. And then, the waste heat recovery. Nanoparticles can be used to develop materials that can capture waste heat from buildings, utilize it for other purposes such as preheating water or generating electricity. This promotes energy efficiency and reduce overall energy consumption. Now, I will be explaining about the challenges and consideration for both nanotechnology and HVAC systems. We start from the nanotechnology first. It has a theoretical restriction because of the peculiar size-dependent features of nanomaterials. Existing thermodynamic models might not adequately represent their complex behavior. Second, the cost and scalability. Increasing the production of nanomaterial through techniques that depends on exact thermodynamics control can be costly and difficult. And the last one is it has an environmental impact. Careful consideration must be given to possible environmental effects of large-scale production and disposal of nanomaterials. All things considered, thermodynamics is a strong tool that supports the creation and advancement and use of nanomaterials. The potential of this combination will surely lead to advances as studies proceeds in a variety of sectors, including electronics, energy, and environmental science, in addition to medical. Now I will be explaining about the challenges and consideration for HVAC system. First of all, it has an early development. The majority of HVAC nanotechnology applications are now in early stages of development. Before widespread usage, extensive research and testing are required. The second one is the cost and scalability. The creation and production of nanomaterials can be costly. One challenge is scaling up production techniques that depends on exact control over these materials' thermodynamics properties. And the last one is the environmental impact. The careful consideration must be given to the possible long-term environmental effect of the large-scale production and disposal of nanomaterial utilized in HVAC system. Now we have come to the conclusion of the topic. Okay, conventional HVAC systems regulate temperatures using well-established thermodynamics principle. Even so, there is still space for development because nanotechnology can manipulate materials at the atomic level. It provides a glimpse into the future of HVAC. This opens up interesting new possibilities by enabling scientists to build materials with distinct thermodynamic properties. HVAC systems that are more energy efficient, produce more comfortable surroundings, and even have a less environmental impact could be made possible by nanotechnology. Still, it's early in the game. To address issues like cost guarantee, the long-term security of these technologies, more research is required. All things considered, the combination of thermodynamics and nanotechnology could completely change how we regulate building temperature, opening the door to a more comfortable and sustainable future. That is all from me. Goodbye!